Thank you very much, Johan. It is indeed an honor and a privilege to be here. And I'm very thank all of you for this wonderful award. It's just amazing. My mother is Dutch, actually, and my father comes from German ancestry, so I'm close to Sweden. Not quite here, but close. So today we'll talk about this long and winding road of technical progress over the last several decades to concrete pavements. Concrete pavements impact, well, all pavements impact our lives more than we really think about it, because there are so many ways in terms of driving comfort and safety, delays, timely movements of products and economic development, defense, communications, you name it. Pavements are there. And it's a challenging time for pavement engineers. I've been involved in pavements now for well over 40 years, and the demands just keep increasing. Now we're asked to design many highways of 100 million heavy trucks going down the design lane over a period of 40, 60 years. Many states now require 40-year designs, others, one or two is up in the 50 and 60 years, and I'll even tell you about one longer than that. So we've traveled down, I always liked music. I was a musician before I became an engineer. A long and winding road, you all know that song, but it has been in every area of pavement, such as design, materials, construction, and it has resulted in a range of performance from fair on the low side to excellent, mostly quite good actually over time, over these many decades around the world, particularly in the US also. And we've learned a lot over these decades. We've learned from experience, I hope. At least we've tried to. From field tests that we've out in the pavement, we have a lot of big experiments where we monitor over many years the performance. So I'll take you on a fast drive down that long and winding road of concrete pavements today, focusing mainly on design. We'll talk a little about the past, starting in the 60s when I started my career, and then moving into the present time, and a little about the future. The incremental mechanistic-based design procedure that has just been developed and is under full-scale implementation now in the US, and a lot in Canada also, that makes the use of theoretical research concepts on one hand, as well as field performance on the other. And we'll talk a lot about that aspect of it. I'm going to just focus, just due to the time series here, constraints on jointed plain concrete pavement. There are several other types. Continuously reinforced is a very common type built in the United States, in Belgium, Australia, and a number of other countries. That's a very good pavement also. Pre-stressed pavements is another type that is starting to be used in very heavy urban areas. And thin concrete, small jointed. I'll mention a few of these things during the presentation. But what I mean by this is what Sweden has built. Basically, you have transverse joints, 4 or 5 meters. They may or may not have dowel bars. You have tie bars. You have slab thickness, all the properties of the concrete. Usually you have a base course and a sub-base over the subgrade. And you have a longitudinal joints right between traffic lanes. And towards the end, we'll talk about putting more longitudinal joints and more transverse joints in and see what that does. The two different kinds of distress types that we really can deal with, actually these three, in design, is transverse joint faulting. As you see at that joint, a step off at every joint. It's a structural problem, and from repeated loadings and poor design. And then we have fatigue cracking that's primarily in a transverse direction, either top down or bottom up. Both of these contribute to roughness, but there's also other distresses related to durability issues of concrete. We certainly still have some of those over the period of time. And construction errors that are made that contribute to some other kinds of distresses like spalling. and longitudinal, but the joints are not sawed properly. You can have cracking due to just poor joint forming. So we'll focus on those two. Let me just say a few words about these two. If you put dowel bars in that are properly designed of sufficient diameter to reduce the bearing stress, you can eliminate faulting as a problem. You can eliminate it. As you see the load approaching that joint, the deflection is very small. Actually, it's 1/2 of what it would be without a dowel bar. So it's quite different. So down below, the base course, there's always water under pavements, it seems like, and it moves whenever there's deflection. But when you have a good shear transfer here, your deflections are virtually equal. You have a very good load transfer, and so the movement of water is very minimal, and you don't really develop the faulting problem. Take out the dowel bar, and you will have some problems if you have heavy traffic. That doesn't mean you need dowels on every project. We have lots of subdivisions of homes and businesses where you do not need dowel bars. There's just not that many heavy trucks. But on most highways, you do. But unfortunately, starting in the 60s, lots of agencies removed dowel bars because it was cheaper. Reduced the cost, right? Yes, temporarily you reduce the cost, but not over the long term. So we have to think long term with pavements. So you see a big deflection here, and as soon as that load hits that other side, there's a big dynamic impact there, and the net effect is water and fines moving this way that lifts up that slab, creating the faulting, the step off at every joint going down the pavement. And you can see that water's under a lot of pressure. We have actually measured that, and it's a couple hundred PSI, which tends to erode just about everything but concrete. So that's something we have to deal with. Here's a picture of a concrete pavement out in California, and where it's drier, much drier, as you hear the news today, all the big fires that are going on out there. But still, look at the pumping and erosion. There's no dowel bars here. There's no concrete tied shoulder. There's no edge support whatsoever here. And you see that there's erosion, and the fines from the cement-treated base are eroding away. And pretty soon you have lots of support out of all of this, and you have no real subdrainage either. And you can evolve into some joint faulting, loss of support, which then can create additional cracking, and all of that causes roughness. Not a good storyline here. So all of these things can be solved in design, and that's hopefully what we'll be talking about in this presentation. Now the other one was the transverse fatigue cracking from repeated loadings. This is a slab that was about 6 meters long in Pennsylvania. It was very, very thick, more than 35 centimeters, and developed within 4, 5, 6 years a lot of cracking, even though it had a tight shoulder. And what caused that? Well, when you start building long slabs going more than about 5 meters, no matter what the thickness is, you create a lot of issues. Particularly, not only the loading is not so bad, but it's the loading combined with temperature gradients and moisture gradients. Most slabs are all shaped like a saucer. They're curled upward. Just look at the shadow under that string line from one corner to another. You can see that that slab is curved upward. And that then means that the weight of the slab plus any loadings that come on the edges of it is going to create a top-down bending stress out here at the edge that can lead to that transverse crack that you just saw. For example, there's a lot of studies that show this. This is graphs from Michigan and Minnesota. Here's your joint spacing, 3 meters long. You have no cracking whatsoever on this project. Both two different projects over 10 to 15 years. But as you increase the joint spacing, you see a little more cracking, a little more, and then suddenly it just takes off. Much excessive. Maybe there's more traffic here, so you get more combination of the stresses combining and interacting together to create more fatigue. So, and this has just been shown time and time. No matter what the thickness is, once you start exceeding a certain length of slab, you start developing cracking. And we never could consider this in design until recent years, which we'll get into in a few minutes. Here's just a little more of an example of that. You can see this is all traffic coming in this direction. This is the approach side, the leave side. You see the erosion mostly here, water shooting out of here, eroding the shoulder. No support from an asphalt shoulder whatsoever. So you get lots of support, and you see a crack is starting there. Even over here, you get some loss of support. And as you look at another slab down that roadway, look how this is eroding along here. And this is breaking off. A wheel load here is a tensile stress right here. Eventually you get a crack. So these are the things we must prevent as we design pavements like this. And providing load transfer, providing thickness, providing good support and drainage for these pavements. Another thing that's happened in the US and probably in other countries is that back in the 60s, we never imagined that there would be this many truck traffic. We assumed 5% of all traffic would be trucks. Well, just a decade later, in the 70s and 80s, it was like 20% or 30%. You know, 3 out of 10 vehicles are trucks now, on many, and even some 50%. So it's unbelievable how much truck traffic, as the economy has grown, truck traffic has just skyrocketed, and it's been true in Europe here too. And not only that, but the weight of the axles has gone up in addition to volume. And then, you know, back in these days, climate was not even considered at all, either on asphalt or concrete, really. There was no consideration on all of these different types of pavements until just recently, as part of regular routine design. There was no way. Such as temperature, moisture, wind speed, humidity, freeze-thaw cycle, solar radiation and its impact on temperature of the pavement, on performance. Virtually none of these were ever considered in design, and that led to a lot of problems. So let's now talk about the present and what we're trying to do, what we have done about them. On one hand, we have theoretical distress models starting in the 1920s with Westergaard. Developing closed form stresses and deflection models. Those were wonderful and helpful and insightful, but they didn't really give us the kind of complexity of loading, especially when it comes to temperature gradients, moisture gradients, that we really needed. And so when finite element came around in the late 60s and 70s, that was a godsend for pavement engineering. So we could consider layers, we could consider joint spacing, multiple wheel loads, the gradients through the slab, all kinds of things like that. And then layers of base course and subgrade. And of course we needed high-speed computers. Even when we were developing this procedure I'll be describing here in 1998 starting, the computer the speed was not that fast. And it would take 30-40 minutes to make a single run on what we were putting together. So that was very difficult to deal with. There have now been developed, and starting in the late 60s and 70s, some really good climatic models that take weather station data, hourly temperatures, wind speed, relative humidity, precipitation, and solar radiation, converts that into temperatures down in the pavement. And we can also model joint loads and transfers, and then really getting a handle on what is the contribution of a base course. Before that, we just assume a spring constant, a K value as we call it. Well, that's not very good structural modeling really, because the base course does a lot more than that. Now, that's on one hand, is all that theoretical modeling. On the other hand, there was a lot of experiments built throughout the country. For starting in the 70s, different states built some, and then we have this long-term pavement performance, a lot of experimental sites, hundreds and hundreds of them. They've been monitored over many years, and lots of data collected on all kinds of cracking and faulting and roughness and many other things. So those two, if you can put them together, they're at the ends of the extreme, you might say. If you can put them together in a marriage, and actually I think it's about the most ideal marriage in the world, put them together, they complement each other. And you take the field performance data, you use that to calibrate structural theoretical models that have been put together that is logically correct. And along with finite element, you put them together and you calibrate the two. And it has been surprising to a lot of people how well that these call them mechanistic based and field calibrated models can actually predict field performance. And that was the goal. If we can predict performance that's out in the field today, add reliability into that, we have a design tool. We really have a tool that can be used. Well, this is the tool, started in 1998. There were many attempts before that did some good work and valuable work, but this was a big team of people on both the asphalt side and the concrete side. I was really fortunate to be on the concrete side and help lead that effort along with a lot of other really, really bright people. Considering the climatic effects, the materials and construction aspects, the structural and the joining, and then putting in the real traffic loads, the whole distributions from small to large of all kinds of axles, singles, tandems, tridems, all of those. Put them together into the finite element model, calculate stresses and deflections, and then compute damage and sum that on basically an hourly basis over the whole period, whether it's 20 years, 30, 40 years, on an hourly, daytime, nighttime, everything reverses for concrete. You have the sun, solar radiation in the day, at night you don't. And they compute damage, and out of that comes a calibration factor, and out comes cracking and faulting too, actually. So just to illustrate that, I'll just go into a few of these aspects very quickly, but in the daytime, you have totally different loading situations. You have hot on the top, cooler on the bottom. The slab wants to look like upside down saucer. At nighttime, complete reverse of that, and then when you have different loadings, you get the top down cracking over here and the bottom up here. And the procedure considers both of them and combines them into a single transverse crack. And then with regard to traffic, all kinds of things from the volume, the classification, all the different types of axles and their load distributions. Monthly, yes, they do vary monthly across, especially on more of the tourist kinds of roadways. Hourly distributions, lateral lane distributions, tire pressure, and wheelbases. All of those are loading or hitting our pavements every few minutes, every few seconds actually. And then for climate, there's a lot of really good weather stations now where we can get literally hourly data on 5 different things, as you see here, that all affect, in one way or another, performance of concrete pavements as well as asphalt pavements. You have to input the water table, and it makes use of that with the soil suction and all kinds of soil models. And then it calculates temperatures at virtually every inch down through the pavements, and moisture contents for all the unbound materials, frost line, the joint opening, closing, things like that, on virtually an hourly basis throughout the design line. So for every layer, you have like 3 different kinds of properties. You have physical properties such as strength, modulus of elasticity, thermal properties such as coefficient of expansion. Boy, that was a shock to a lot of people how critical the concrete thermal expansion was. People hardly could believe that with limestone you have very low, with other sources of aggregates like chert you have extremely high, or river gravel, 20% higher, 30% higher, or even more. And so that affects cracking and faulting and joint opening and closing big time. And then you have hydraulic for the unbound types of materials here, the movement of water and the impact of that on modulus. So created an incremental model that starts out at time 0 and starts incrementing. Because why is that? Because traffic in the first year is lower typically than it is out here many years from then. So every month the traffic will vary. The concrete strength, the modulus, and modulus varies. Shrinkage varies too. I really should have put that on here too. The modulus, if you have an asphalt base course, That's going to go up and down with the seasons, isn't it? Even on a daily basis. Have an aggregate base course. It's going to vary depending on moisture content and frost moving through it. Subgrade, it'll have the same situation. In the winter it'll be frozen, the spring it'll be thawed. And then every day you have axle loads pounding on that pavement. It's really a complex situation, isn't it? Pavements, people think pavements are rather simple structures. Well, it's just not so. It's absolutely not so. It's an extremely complex system. And if we really try to model it, then it's even, more complex than this by far. And as time goes on, more theses, more research, it'll improve on all of this stuff. This is just a draft, really, of the complexity of it. With our finite element, we can model virtually any kind of loading and put that into an algorithm, such as for cracking, as shown here. Calculating our critical stress, put it into like a fatigue algorithm, such as Miner's fatigue damage is what we have used quite successfully, and I'll show you how that is in a moment. And then we calibrate that, the Miner's damage versus field cracking. That gives you then the tool that you can use in design. This is some of the sections in Canada and the US of different kinds of concrete pavements that were used in this calibration, so they're spread from cold to warm, wet to dry. So it's a big mix of climate. And here's one of the first major models that was developed, calibration. So this is the equation here, fatigue damage as a function of cracking. And here's the measured cracking, that transverse that you saw on that slide. And there's a lot of data points, starting new, the pavement, and then as time wears on, some of these have 10 data points in one section. So we have about 522 observations. As you see, you get up here, some slabs, every single slab is cracked. Variation is a big factor of pavements, and that's why there's a lot of scatter. But we use that scatter to do the reliability analysis. We can do a confidence interval and different reliability, like this is the 50th, 60, 70, 80, 90, 99, that I'll show you in a moment. So that's this is the critical curve right here. And so in design, you put in a trial design and you calculate over time how much fatigue damage, and then you come up to the line or to the reliability, you say 95%, which would be up here. This is the 50th. And if that's too much cracking, you say, I have to modify it. I have to put better base course, a thicker slab, more tied shoulders, or things like that, more dowel bars. Just to illustrate, here's the critical. If you have a single axle, if you have multiple axles, it's top down. So you model them both. So now we can directly consider a tied concrete shoulder and the load transfer as these wheels roll down this pavement. How much of that is sheared off, taken by the shoulder, and how much of that has to be absorbed